Alright, so we've talked a lot about Silo theorem, so let's move on to something else. And this is going to be the topic of composition series. So, well, first of all, before I get there, I don't know if I used this terminology in one of the last videos, but I use this terminology of a simple group. And we never really talked about what that is, so I should probably specify that. A simple group is a non-trivial group with no non-trivial normal subgroups. Okay, so when we say a non-trivial group, we mean that the group is not just the one element group consisting of only the identity element. And when we say no non-trivial normal subgroups, what we mean is that any normal subgroup is either going to be just the identity subgroup, i.e. it's just the element E, just the identity element, or it's going to be the whole thing. And certainly we call those trivial normal subgroups because in any group, the whole group is normal and the identity element is normal. Or the subgroup consisting of only the identity element is a normal subgroup. And you can check those, they're very easy to check. And if those happen to be the only two non-trivial, the only two normal subgroups in a group, then the group is said to be simple. So anyways, just stating that out there so that we can use that in the future if necessary. And we're going to move on to composition series now. So a composition series, and this is going to be of a group G is, what is this? This is a sequence of subgroups. And we might call this, we'll denote it by sigma for series. And then this, we're going to have G, which is equal to G naught. And then this is going to contain G1, which is going to contain all the way up to, let's say, Gm, which will be the identity subgroup, where Gj plus 1 is normal in Gj for all, let's say, j between 0 and n minus 1. So what this means is G0 is, G1 is normal in G0, G2 is normal in G1, all the way down to Gm being normal in Gm minus 1. And so sometimes when we're writing a composition series, instead of writing out like, let this be this and suppose that every single one is normal, we might just replace all of these with normality triangles. But of course they're going this way because these ones are normal and these ones. It goes the other way. The same way as in the inclusion. But anyways, that'll just be a shorthand. Okay, so this is a composition series. The ith graded piece, and graded piece is the definition here, where, see here, so I is between 0 and n minus 1 is, let's see here, we'll gri and then put the sigma on top G. And sometimes if the if the composition series is understood, then we'll just call it GR sub I of G. And this is equal to GI mod GI plus 1. And so certainly this is a group, because GI plus 1 is always a normal subgroup of GI. That's part of the definition of a composition series. And so because we have these normalities, each of these graded pieces is actually a group. And so yeah, this is the definition. One thing to keep in mind, so I call this a composition series. I believe this is the terminology that's used by Bourbaki, but this is not necessarily a standard definition. Some people use composition series to refer to like a more specific type of what this is called in a composition series. So even if you look at my previous videos and like my Jacobson exercises and some of my other algebra exercises, you'll see me refer to things that look like this, but I won't call them a composition series. I'll call them a normal series, or I'll call them a normal tower, or I'll even call them a filtration. Let's see here. I took a similar class to this, and we referred to them as filtrations or normal towers. And then in Jacobson will refer to these as just normal series. And then also the other thing is I also refer to composition series in those cases as something more specific, but we'll get to that. So anyways, in these lectures we're going to use, and not only in these lectures but in the exercises that are associated with these lectures, I'm going to use composition series to refer to this. I'm not going to use filtration. I'm not going to use normal series or normal tower. Okay? Let's do an example just so that you can see what this might look like. Let's take G as Sn, and this contains, let's say, An. We know that the alternating group, I still don't think we've talked about, like, in full detail the alternating group. But you can, like, if you've seen group theory before, you've probably talked about it, and we'll probably talk about it at some point in this course. But these are the collection of permutations on n elements. An is the set of even permutations, and you can look up what precisely I mean by even. There's a very specific definition, as you should expect, since this is mathematics. And so this, and then certainly this contains the identity. And so you can prove, it turns out that An is normal in Sn, and obviously this is going to be normal in here. This is always going to be trivial because the identity element is normal in every single group. Alright, so that's that. And so that's, I mean, this isn't a really, there's nothing really interesting about this example. It's just so that you can see what one of these might look like. Okay, so this is a new concept, so we've got another definition. So, given two composition series, we'll say sigma G equals G naught, which contains G1, all the way up to Gn, which is trivial, or rather just the identity. And we'll say sigma prime, which will be G, but this here will be G naught prime, which contains G1 prime, all the way down to, let's say, Gm prime, which is the identity. We say sigma prime is finer than sigma if sigma, okay, so sigma prime is finer than sigma, what that means is that we can obtain sigma by throwing out some of these terms in sigma prime. So if sigma can be obtained by discarding elements of sigma prime. And when I say discard, I mean, like, for example, maybe instead of having, let's see here, so let's see here, if sigma is obtained by discarding elements of sigma prime, so sigma prime is going to have, the finer one is going to have more things in it. So what we could imagine is maybe sigma of prime, we've got g naught prime, contains g1 prime, contains g2 prime, but if you write this in terms of sigma, then sigma, maybe g naught is equal to g naught prime, but g1 here is equal to g2 prime. So it skips, you remove g1 prime. And that's still going to work because, let's see here, the fact, see here. So if you've got, so you can't just throw out elements in a composition series. Like you might have something where like you might have like G2 prime is normal in G1 prime, but it might be the case that G2 prime is not normal in G. Because remember, the normality condition, when you go from G1 prime to G naught prime, is the condition is stronger because you have to satisfy the condition for a larger collection of elements because G naught prime contains G1 prime. So you can't always just take a composition series and just throw things out of it and get a less fine composition series. But sometimes you can. And if you can, then you can have this scenario where one composition series is finer than another. Okay, so let's say this more precisely. So more precisely, n is less than or equal to m, right? Because the finer one has more things in it. See here. And there is an order-preserving injection so here this injection will go from, we'll call it phi, it'll go from 0 through n to 0 through m, such that G, no, that's not a G, that's a phi. So Gi is equal to G prime phi, no, this, it looks like an E in my notes because phis look like E's a little, but it's not. So phi of I. Okay, and you can see that that if you do this process of just discarding some of these elements to get a different composition series, then certainly this m is going to be greater than or equal to n, and then of course if you associate with these indices, the ones that, well rather for each of these you can associate one of these indices, and you don't need to associate all of them, but you can't, it has to be order preserving, and you have to, it has to be injective. You can't have G naught being equal to both G naught prime and G1 prime. Although I guess in some sense, we didn't really specify anywhere in here if these are required to be strict inclusions. So, yeah, but in any case, you can make this an injection. Okay, and then let's see here. I think we have time for one more definition, and then I think that might be all for this video. I don't think I'll be able to get into any sort of more enlightening examples. But anyways, so we have a definition. So sigma and sigma prime are equivalent if, and I'm going to use the notation from the bottom here. So n equals m. And so, of course, what I mean here is that, we write sigma in this way, and we write sigma prime in this way, and then n and m here are the same, meaning that they have the same number of elements, and there is a sigma, which is a set automorphism, or rather an automorphism on the set of n minus 1 elements. Oh wait, no, this is n elements. But the indices from 0 to n minus 1 such that the ith graded piece in sigma of G is isomorphic to the sigma ith graded piece in sigma prime of H. Yeah. Okay, so I guess here we have H. So I guess I lied earlier. Sigma prime. Oh wait, no. Do you know what I could do? Oh no, I do have to make it H, because sigma prime is H is equal to H naught contains all the way down to HM equals E. Because the important thing here is that G and H don't have to be the same group. They just have to have the same, they just have to satisfy this property, which is basically that you can take these two groups and, or rather you take these two composition series and they end up having, you have the same number of subgroups in each composition series, and even though you don't need to have G naught isomorphic to H naught and G1 isomorphic to H1 and so on. You don't necessarily need that, but you do need the graded pieces to be isomorphic up to reordering. So you have G naught mod G1 here as one of your graded pieces, and so there's going to be some HI mod HI plus 1 here that's going to be such that these two are going to be isomorphic. And this map that assigns this graded piece to this graded piece, when you consider that over the entire collection of graded pieces, is going to be a bijective map because it's a set automorphism here. Okay, so no, I am out of time now. So anyways, there we go. And we are then going to discuss some more stuff about composition series.